Hello and welcome to MIPI DeFi testing in automotive application. I'm Pascal Grison, application engineer in Tektronix, and I will get you through that web seminar and we will address the pitfalls in MIPI DeFi testing and how you will overcome the test challenges with Tektronix solutions. I will guide you through MIPI DeFi pitfalls. MIPI DeFi is a complex bus involving impedance switching with speed switching, and the right probe is critical to make that type of measurement. I will show you the probes, and at the end of the presentation, we'll get through a quick demonstration of the compliance test application running on the oscilloscope. Let's get started.
Hello and welcome to Tektronix Academy. My name is Pascal Grison, and we are going to talk about MIPI DeFi testing in automotive applications. First off, we're going to take a look at how different MIPI standards are slowly but surely being adopted within the automotive industry. In this section, we'll cover the different drivers around information sharing and safety that require more and more highly reliable databases. Next, we'll take a look at the DeFi specification. We'll look at where it sits in the world of MIPI and how it fits with other specifications such as DSI, CSI. Then we'll take a look at some of the unique features of DeFi signal that make it power efficient, but also raise some signal integrity challenges. After that, we'll dive deeper in the DeFi specs and look at the test requirements around the standard. I will briefly cover the test strategy for MIPI in terms of DeFi, as well as talking about the range of measurements and equipments needed to perform these tests. In the last two sections, I will look more closely at the tools and steps required to make measurements on both the transmitter and receiver using the solutions from Tektronix to frame how these tests are completed. Before we get going, I'd like to point out where I will be pitching this presentation will not be covering the protocol layer in any major details or talking about how pixel information is transmitted back and forth between devices. Nor will we be spending much time talking about how to design DeFi interfaces. There are plenty of contributors in the MIPI world who can talk about these topics. We're going to stay focused on what testing is required and what it takes to get your chip or part certified. First up, we're going to take a look at the growing adaptation of MIPI in the automotive world. Electronics is becoming a greater and greater focus of automotive R&D budget spend in many Tier 1 manufacturers. Both top car manufacturers and Tier 1 suppliers have quickly realized that giving value-added features to their customers is key driver of profitability in market. This innovation has caused a snowball effect where end customers are expecting more and more digital comfort in their new vehicle purchase. Coming hand in hand with increased electronics in vehicles is the need for more sophisticated communication buses such as those from the MIPI Alliance. There are effectively two core areas of innovation causing the acceleration adoption of MIPI bus standards in vehicle. The flow of information to and from the vehicle and within the vehicle is the first area, while the second is around the safety systems and the march towards autonomous vehicles. Overall, there are many needs in the automotive industry that are common with the mobile industry where MIPI was originally designed for, such as the greater integration of sensors, cameras, and displays within the ecosystem. This, in turn, drives the need for higher and higher bandwidth throughput, with the added complexity that a wide variety of speeds are required. Other similarities are that cars are traditionally closed systems and are sensitive to power consumption's level as this impacts fuel efficiency. What's different is that the automotive industry typically requires greater reliability in systems, often 2 orders of magnitude better than the smartphone industry. Components and parts are required to last a lot longer in more harsh environment, decades versus few years in the mobile market. Information flow can itself be split into 2 areas. The first is telematics, which is your GPS system for tracking, location, and guidance. The information in your guidance system ultimately needs to have a human interface in the form of a display. Then we have in-vehicle infotainment, IVI. which are things such as audio interface for radio or voice control, Bluetooth connectivity, internet access, and displays for video. These displays are becoming more and more sophisticated these days in terms of what they are showing the driver and their quality. Users of premium vehicles now expect smartphone level of quality when it comes to touch interfaces and resolution. This trend is moving down through the car company product lines and is expected that digital dashboards, for example, will be over 50% of all vehicles in the early part of the next decade. To highlight that, you have to notice that most, if not all, the new vehicles produced have now a rear parking camera. Already today, some cars have the ability to give a full 360-degree view of the car position through the use of at least 6 strategically placed cameras around the vehicle. What do all these applications have in common? Well, there is a need to transfer a huge amount of sensor information from cameras to a processing unit. Secondly, there's a need to manage the transfer of pixel data from that processor to a high-resolution display. Both of these common tasks are required in the mobile space, and the MIPI Alliance for many years have been supplying a series of physical and protocol layer buses specification to address these needs. In the safety and autonomous driving space, there are similar challenges. In the past, safety systems were very much passive and reactive, such as the airbag, which would deploy on impact protecting the passengers, or the crumpled zone, which is a mechanical design to absorb and dissipate the force of an impact before it reached the occupants. Now, electronics are being used to help move that philosophy to a preventive mindset. Cars are starting to deploy Active Driver Assistance System, or ADAS. This includes features such as adaptive cruise control and lane departure prevention to automatically ensure a safe distance between your car and the surrounding vehicles. Safety improvements are based on the desire to build a 360-degree sensor shield around the vehicle. This shield takes the form of cameras network, range and velocity radar systems, or other methods such as LiDAR or ultrasound, all of which contributing to different safety systems in the vehicle. Communication too is paramount. Many countries and organizations, such as the EU, have the desire to see the car as part of an integrated communication network for the transport industry, sharing critical data for safety but also in an attempt to reduce congestion and emissions. What does that mean in reality? Well, it means a national communication grid where the vehicle acts as end node, receiving information from traffic monitoring system and other vehicles. V2X is the term often used to symbolize a vehicle connectivity into this grid. In many cases, that will mean the integration of wireless transceivers into the vehicle, which will utilize both custom and existing wireless networking infrastructures. Autonomous driving system, ADS, is the ultimate goal here, and probably most surprising thing is how quickly it is happening. I'm sure we all keep half an eye on success of Waymo from Google or Tesla autopilot projects in the news, but even in today's family cars, we already get self-driving features success as parking assist. The image below, courtesy of the MIPI Alliance, show some of the many different sensors and interfaces on a modern car and how MIPI themselves have specific transport buses to support the different speed and power requirements. For safety applications, the needs are very similar to infotainment. There is a need to transfer sensor information from the periphery to core processing engines within the vehicle. These sensors could be in the form of cameras, but very often suppliers of other sensor systems such as radar are deploying MIPI specifications like PHY are their digital interface with the central processing systems. In many cases, the safety system also requires the display of processed information. The other attribute of safety and autonomy in vehicles is the mix of both low-speed and high-speed data transfers. Again, this has many similarities with the mobile space, and the MIPI Alliance caters for this with a wide range of bus standards and scalable speed performances. For example, the CSI and DSI standards are used for the transfer of video information from cameras to processing units or from the processor to the display. You can also find I3C, a low data rate, low pin count bus. Or, for the networking side, MIPI have protocol standards such as DiGRF for interfacing with wireless modules. So far we looked at how the electronics is evolving in the automotive market. We suggested how the MIPI is servicing these needs for higher data transfer speeds while reducing power consumption and pin count. I hope I've made clear so far, but in case it is not, I will state explicitly that MIPI isn't a bus standard in itself, but is a family of bus standards, each tailored for a particular job. We've also seen how the camera and display are at the heart of the current and next generation smart car, and the MIPI Alliance covers this area as well, with the DeFi bus being one of the most popular interface adopted. So I mentioned at the start of the presentation that I would not be speaking about the protocol layer specifications in this presentation. I'm going to quickly break this rule just for one slide, as it is important to understand the context of our physical layer standards, such as DeFi, to better understand the different modes of operation that DeFi runs in. There are two core specifications that are used to define the protocol layer structure between two elements, CSI and DSI. CSI, or Camera Serial Interface, is on its second release, or CSI2. It takes care of pixel and frame information being transmitted from a camera to a host processor. DSI stands for Display Serial Interface and transfer pixels from the host to the display. These protocol layer standards take care of pixel and byte packing and unpacking. They define the low-level protocols used to synchronize transmission between the transmitter and receivers with packet structures including header information and CRC checking. They are part of the scalability of the bus by managing the deserialization/serialization of packet data on multi-lane implementations. The physical implementation is handled by other specifications. In the case of our presentation, we are focused on the DeFi version, but these are others. The application layer handling is beyond the scope of this presentation altogether. On the right-hand side, you can see some of the characteristics of the CSI2 bus structure. It has two operating modes. One, a low-power mode, where little or no information is being transmitted. This could be the blanking region of a video frame. And it has a packet transfer stage which could contain active video information to continue the example. Here, high-speed throughput is required. Data is packetized and there is the ability to send both long and short packets out to the receiver. When there is little or no information to be transferred again, the CSI standard manages when the PHY switches into and out of its low-power state, saving on power consumption. One of the great strengths of the MIPI is that the designer can choose the physical layer interface that best suits their implementation. For CSI2 and DSI, MIPI has defined three specifications. DeFi was the original and delivers the best balance between power and data throughput. It is also the standard that has gained most popularity in the market to date. CFI can manage greater data throughputs for a smaller number of pins by employing an encoding scheme that transfers multiple bits per symbol. While MIPI has the faster raw data rates and maximum throughput for the same number of lanes, it is the more power-hungry and requires more complex implementation, so it is only used for the highest performing applications. Here is a comparison of the three PHY layer bus implementations. I'm not going to go through each line in detail, but just to point out some characteristics of each. MIPI, for example, employs a bidirectional bus network with NRZ encoded signaling and embedded clocking. Version 4.1 of MIPI standard calls for roll line rates of up to an incredible 11.6 gigabit per second. This is clearly for the performance market. CFI uses a unique combination of 3 wires to encode symbols onto the lane. DeFi, the focus of our presentation today, has released version 2.0 of its specification, increasing the individual lane rate up to 4.5 gigabit per second. However, today we are going to focus on the version 1.2 of the specification, as it is the most widely deployed and implemented version. It has variable data rate of up to 2.5 gigabit per second on a single lane. The objective of DeFi is to describe the electrical and interconnect specifications between transmitter and receiver of either a camera or display interface. The bus is a source synchronous master-slave implementation, meaning that a clock signal is supplied from the transmitter to the receiver. While the DeFi specification does allow for the direction of data being transmitted to flip, in general most implementations have one direction for their high-speed data transfers. That means for camera, the camera itself is the master and transmits sensory data to the host, which is the slave. For displays, the host is the master supplying the clock and the display is the receiver. Each link has a clock signal and at least one data lane. The data is clocked on both the rising and falling edge. This is referred to as double data rate clocking or DDR clocking. One of the standout features of DeFi is that it has 2 operating modes, a low power mode or LP mode, which is described as a high voltage unterminated signaling bus. This mode is usually deployed when it is not required to transfer large amount of data from the transmitter to the receiver. High-speed mode, or HS mode, is a low-voltage differential signal where the bus exhibits the effect of a transmission line. Therefore, both ends of the communication link must be terminated. During normal modes of operation, the PHY must actively switch between these 2 operating states based on instructions from the protocol layer in the case of the transmitter and the state indicated on the bus in the case of the receiver. The standard also has the unique characteristic in that when in low power mode that each clock and data line acts as a single-ended signal to ground, while in high-speed mode, a pair of signals work together to create a differential path for the data transmission. As mentioned earlier, the line rate in differential mode is 2.5 gigabit per second, but links can be scaled upward to support higher throughput by using multiple lanes. It isn't uncommon for camera displays or hosts to support a clock lane and up to 4 data lanes. It is optional for the clock lane to transition in and out of HS mode, like the data lane, or the specifications support the clock remaining in a continuous high-speed mode. In the bottom example block diagram from the DeFi specification, it shows how the system could be implemented with separate LP and HS blocks within a single PHY and active switch linking the 2 onto the same transmission line. This coexistence of the 2 modes on a single bus line lead to issues of termination switching and the receiver's ability to reject the glitches that ultimately comes from this switching. Now let's look closer at the AC and DC characteristics of a DeFi transmission. Anyone who studied the DeFi specification will be familiar with the plot at the bottom. It depicts the signaling levels for the 2 core states. Firstly, you see the 2 signal lines in action, D+ in blue and D- in green, which will have very unusual signal levels. During low power mode, each signal is working independently of each other, single-ended mode. Here, the signal swings from 0 volt to 1.2 volt nominally. It also has stringent controls on the rise time of the signal in order to reduce the impact of EMI generation from the DUT. This combination acts to limit the current being drawn during this stage and in turn conserves power. In high-speed mode, the signals now act together as a low-voltage differential signaling. The differential swing voltage is in the regions of hundreds of millivolts, and the signal typically contains a DC offset of common mode voltage in the region of 200 millivolts. In this mode, the signal has fast switching capabilities in order to greatly improve the data throughput, and the differential mode gives these small signals common mode noise immunity. In low power mode, the signals remain unterminated at the receiver or at high impedance termination, while in HS mode, each signal leg is terminated into 50 ohm in order to minimize impedance mismatch reflections and improve the signal integrity of the small signals. This is very common for LVDS signals, but it poses a challenge to probing, which we'll discuss later in this presentation. To help understand some of testing requirements, it is important to look a little deeper into how the DeFi signal transitions from LP to HS mode. There are 4 states that a DeFi bus can occur during normal operations. LP11 is the LP state. It also referred to as the stop state. The bus will remain in LP11 as long as the data is not being transmitted. LP01 is where the transmitter starts its transition from LP mode to HS mode. LP00 is the HS mode. It also represents the final transition period from LP mode to HS mode. It has a minimum settling time, which is used by the receiver to switch to receive HS data. During the LP00 state, the transmitter also transmits a synchronization pattern in HS mode so the receiver can train and disque between the clock and data lanes, indicating to the receiver to prepare to receive HS data. LP10 is the opposite and comes after HS data burst and is where the transmitter requests the receiver to prepare to return to LP state. Finally, there are 2 other special states the bus can take, which I won't cover in any detail. These are the escape mode and turnaround mode. The minimum duration that a bus can be in HS mode is 1 byte, and there is no maximum duration. From a signal integrity point of view, it is critical that the device transitions from LP to HS mode in a smooth, monotonic fashion without glitches, and that the receiver remains terminated during the HS mode. Other causes for concerns are the larger number of global timing specifications that must be characterized on a device to ensure interoperability. Examples of these are the HS0 and HS trail timing values, which are minimum leading and lagging periods in the LP00 that the transmitter must remain in order for the receiver to reconfigure the new state. So we're taking a look at the characteristics of DeFi signaling, and we've looked at some of the challenges and requirements around these signals. Now let's spend some time talking about the process for ensuring your product conforms with the MIPI standards, the required measurements, and some of the test challenges. This slide is to help you understand the process of gaining conformance with the standards and the different terms and documents used in that process. The first thing to say is that there is no such thing as compliance with MIPI. They do not certify products. Within the MIPI Alliance, you have the main MIPI organization. It sets the goals of the body and gathers together different industry experts to work on defining individual standards. This could be CSI or DSI specifications, for example. Then they set up subgroups within MIPI called working groups. Each group will have specific tasks and mandates to define and refine specifications. For example, we have the DeFi working group, of which Tektronix is a contributory member, that have the ownership of the DeFi specifications. The DeFi working group will then produce a document called a Conformance Test Suite, or CTS document. In many standards, this document is used to specifically outline the test methodology and procedures needed in order to ensure that a product is passing a specific specifications in the standard. This document becomes the master reference document for all measurements methodologies. Once the CTS document is defined, all the test equipment vendors will write a procedure on how each individual measurement is implemented on their equipment. This document is called Method of Implementation. Each MOI will include specific model and part numbers as well as any accessories or software tools required to complete the CTS measurements with their tools. It also details each step required to configure the test setup for each measurement. These MOI documents are then shared and reviewed by the working group before approval. Finally, the design and validation working on a product will test this product to the CTS requirements with their chosen test and measurement vendor's equipment using the MOI as a guide. In many cases, the test and measurement vendor will offer automated software to simplify this process. Once testing is complete, the producer will fill in and submit a compliant test report to the MIPI organization, proving their product meets the CTS and is compliant with the standard. In the case of MIPI standard, the product can then be registered as a compliant product. Well, how many measurements are contained in the CTS documents for DeFi 1.2? In fact, there are over 100 measurements stipulated between the transmitter and receiver. Many of these measurements must also be repeated in implementations that have multiple data lanes. So we are looking at a large range of time-consuming measurements to be made. Now the good news is that integrators often only have to test a subset of these measurements. For example, if I produce a camera chip or module, then I'm only interested in making the transmitter measurements. In terms of measurements, there are 3 core sections of testing. First, there is the transmitter timing and signaling section. These contain 6 groups of tests in total. Group 1 and 2 cover the basic LP signaling measurements for both the clock and data. These include such things as DC levels and rise-fall timings. Group 3 and 4 cover the high-speed signaling measurements, again for the clock and data. This includes measurements such as the differential and common mode signal levels and matching, and some of the timing measurements such as the HS prepare and exit times during the LPHS state transitions. Group 5 looks at the relationship between the clock and data signals during HS mode, while Group 6 some miscellaneous timing measurements. In section 2 we move to receiver measurements. The first 2 groups detail the receiver's ability to handle differential voltage and pulse width conditions, as well as the response to low-level protocol commands. Groups 3 and 4 details complex measurements involving the receiver's ability to withstand borderline setup and hold conditions, jitter, and voltage noise, as well as tolerances to different state timing conditions. The final section covers the impedance and S parameters profile of the transceivers during low power and high speed modes respectively. All of these test requirements lead to some specific challenges that are unique to DeFi testing. Firstly, there is probing. The fact that the signal's impedance changes with states mean that the probe must be able to handle both 50 ohm and high Z state in order to ensure that the probe doesn't load the bus incorrectly. In many applications, it's also required that soldering probing must be used in order to access to the signal in tight setups. No 2 implementations are the same. Some setups require multiple lane testing, which impacts the amount of total test time, while other tests require flexible triggering setups for greater insight. And on the receiver test side, you need a flexible solution that can simultaneously generate both 4 single-ended signals and 2 differential pairs for the clock and data signals in order to generate both LP and HS modes. Finally, there are stringent requirements to calibrate the signal generators in terms of noise and jitter in order to stress the receiver on the test. A test solution needs a simple yet powerful solution to do this. Now let's take a look at what tools there are required for transmitter testing and what solution Tektronix has in this area. Now we'll look at a couple of possible test scenarios. None of these are strictly stated in the MIPI specification or CTS themselves, but they give an idea of the potential test setups there are out there. The first setup could be described as a live setup involving a chip-to-chip scenario. Here we're simply making a mid-bus probe onto our 4 signals using our high impedance probes. Signal termination is supplied by the receiver itself. The second possible scenario is a non-live setting between a chip or module and a dedicated termination board, such as the one you can source from UNH or Moving Pixels. Often in this scenario, the signal is routed from the transmitter via SMA cables into the termination board, and the signals are probed at dedicated test points on the termination board. A third possible scenario is again a non-live setup, but in this case for a multiple lane system. Here, each of the lanes are routed into a high-performance RF switch matrix, and then 4 of the critical signals, the clock and any one of the data pairs, is routed into the termination board. Care must be taken to remove the lossy effect of the switch and to ensure that the cabling does not introduce significant interpair or intrapair skew to our measurement. As mentioned before, the bus transitions between a IZ or unterminated state during low power mode into a 50 ohm in high speed mode. The low power mode will require the probe to have a high impedance in DC, while the capacitance and inductance in the probe tip will cause the probe impedance to roll off as the bandwidth increases. In many 50 ohm LVDS signals, a flat impedance is desired for minimal impact on the signal edges. Often, the impedance response of the orange or light blue trace is deployed in many high-performance probes. This response, however, will cause waveform distortions during the critical low-power to high-speed switching stage. The dark blue impedance response on the top plot is the ideal solution here, such as the one from the Tektronix P7700 probe series. This will yield the yellow waveform on the bottom plot, which contains less distortions when compared with the light blue waveform. The P77 probe was designed with D-Fine in mind. It has high impedance, low capacitance design, which minimize loading on the signals. To complement for this electrical response, the P7700 probe also has some industry firsts. For easier signal access, it employs a unique flex circuit capability, making it easier to solder to signals. Each probe and probe tip also contains its own S parameters characteristics, which automatically de-embed any residual loading effects from the probe, ensuring that you see a calibrated signals right down to the probe tip. We've also spent significant resources in reducing the cost of the probe tip by an order of magnitude down to well below $100 per tip. Finally, it also includes a unique tri-mode feature that allows the user to view the differential, single-ended, and common voltage waveform simply with a press of a button. So, in the endeavor to build a perfect probe, we're a bit at an impasse. A Z-active design would give us better eye diagrams in high speed, but we would lose some DC accuracy for the low power measurement. The traditional probe, on the other hand, is better for high impedance drivers and more accurately replicating the DC levels of the signals. There is a solution. By combining the traditional probe's impedance response with DSP correction filters built in the scope, we can effectively de-embed or unload the eye diagram that we see in the oscilloscope. We do this by taking the S parameters, so the return loss and insertion loss of the probe tips, probes, and scope input channel, then creating an inverse filter to remove this loading and distortion effect on the signal after it has been digitized by the oscilloscope. How does this process work? First, we start with a frequency response that we desire. Next, we measure and characterize the S parameters of the tips, probe arms, and scope inputs. Tektronix is unique in that we measure these characteristics of each component during manufacturing and store their S parameter data within each component of the measurement system. During runtime, we cascade the S parameters data together and then create an inverse or correction filter for the measurement system. Then we store this filter as the coefficients of an FIF filter within the oscilloscope. When the oscilloscope samples the signals, we convolve the filter with the incoming samples during the acquisition, effectively removing the probe's effect. A unique part of Tektronix's solution is that this process is completely automated and seamless. When you plug in a probe tip and probe into the scope, it will automatically download the S parameters for that individual item, creating the filter and applying it to the signal. There is no action required by the user. Now let's look at this theory in action. First, we take a reference signal captured without the probe. This is an 8 gigabit per second signal. Next, we add the probe to the test board. At the device receiver, it will be loaded by the probe and the signal will be slightly distorted. This second eye diagram is representative of the eye that your receiver will see. We've used the eye accuracy equivalent time scope to act as a golden receiver in this case. The next eye diagram is the loaded eye that you will see on the measurement oscilloscope. It is similar to the RX eye, and as before, you can see the impact on the edge of the signal. Finally, once we apply the de-embedding filter to the signal, we see the unloaded eye on the scope. It closely tracks the original reference eye diagram in terms of shape and amplitude. Note that we'll see some extra noise and distortion on the unloaded eye when compared to the original eye on the top left. This is due to noise and distortion being added by the probe and scope. At the end of the day, we are still not perfect, but it very closely matched the original signal. So basically, tri-mode probing is the ability of the user to be able to see the different signal between V+ and V-, the single-ended signals coming from V+ to the ground or V- to the ground, and the common mode signal, all with the simple press of a button on the probe compensation box attached to the oscilloscope. Tri-mode probes employ these different amplification options within the probe in order for you to fully characterize or debug your serial data signal. This is done by routing a third signal, the ground, to the test point via the probe tip. Many serial bus standards such as serial ATA, PCI Express and USB require differential and common mode measurements to be made. Historically, you needed to use two probes to access the negative and positive signals simultaneously. With tri-mode probing, we can do this with a simple click of a button. For those of you out there making measurement on memory buses such as DDR, another example of how tri-mode probing can help you is with accessing multiple DQ signals from a single BGA with a single probe. In my pictures on the right-hand side, I've circled a probe that is probing DQ0 and DQ1 at the same time. A user can make measurement first on DQS to DQ0, then switch and make measurement between DQS and DQ1. For overcoming the challenges of automating so many tests, Tektronix supplies a software tool called TechExpress DeFi TX. This provides conformance and characterization testing for all CTS 1.2 measurements. This tool includes an automatic gating feature that isolates the HS and LP portions of the waveform. It can also handle features such as multi-lane measurements, custom limits, test reports, and much more. Here are some examples of those features. For multi-lane, we incorporate the automatic control of a Keithley RF switch, making a single button measurement. The software also supplies the ability to add de-embedding to remove the effect of the switch. These are DSP filters with the inverse of the switch frequency response, which are applied to the incoming signal. This feature is also used for removing the effect of high temperature probes that might be used during temperature characterization. The software will automatically place cursors to gate the LP and HS states during testing. However, the user can switch into manual mode during testing to adjust this if needed. In the final test report, it will include a screenshot of the waveform and the cursor position for the reviewer's reference. Also included in the test report is not only the pass-fail result, but the margin between the test result and the specifications limit. To complement the automation tool, Tektronix also includes a debug and analysis tool called DeFi Essentials. This is effectively a library of setups within Tektronix industry-leading jitter and eye analysis engine called DPOJet. This will quickly invoke the required setup from the library and allow the user to tweak and adapt the setup for their requirements. This tweaking could include customer trigger settings for corner case or non-compliant measurements. Here you can show an example of Essentials capturing a HS burst. It's hard to see in the diagram, but the burst also has a set of cursors which are gating the measurements to only include the HS bursts and not the LP states at either end of the waveform. The user then added an eye diagram to the measurements along with their own custom mask. This gives extra insight to the signal HS condition that is beyond what the standard calls out for. Another advantage of the Essentials package is that it can be purchased separately from the automation package and can provide a much more cost-effective solution than the one of the full solution. The first thing you need for testing is a 4-channel oscilloscope. The scope must have at least 8 GHz of bandwidth to support the fast data rates of up to 2.5 gigabit per second. Bandwidth control is also highly desirable as the combination of measurements include slow, low-power signals and fast, high-speed signals. With your 4-channel oscilloscope, you also require 4 high-impedance, low-capacitance probe with bandwidth matching the 8 GHz of the oscilloscope, and with a wide dynamic range to capture the 1.2 volt low-power signals, while having low noise performance for the high-speed, low-voltage differential signals. You must be able to capture simultaneously clock plus, clock minus, D plus, and D minus. Some TX setups may also require the ability to dynamically switch termination of the bus line from 50 ohm to high impedance settings. This is particularly true when testing chips and modules. There are several options on the market for this. Tektronix recommends termination boards from either the University of New Hampshire Interoperability Lab, called UNH, or from a company called Moving Pixels. These solutions often include test points where probes can be easily soldered to the signal lines. The final feature required is in your device under test. The user must have the ability to force the device to transition into and out of HS mode on command in order to capture the appropriate signal for test. Usually, this is straightforward for implementers to do, but you must work with your PHY vendor if required. MIPI do not stipulate any method or tool for doing this. This slide shows a summary of the solution for TX testing from Tektronix. We have DPO or MSO 6 or 70,000 with 8 GHz for DPHY 1.2. You will also need 4 of the Tektronix revolutionary P77 performance probes delivering the highest signal fidelity in the market. Next, you need the termination fixture, either from the UNH or Moving Pixel, both of which can be ordered through Tektronix. Finally, to automate measurement and allow for debugging, we have our TechExpress DPHY TX software and the DPHY TX Essentials software. Now that we had a look at making TX measurements, let's take a look at our last section, which is the receiver testing. As data rates have become fast and faster, and as interoperability is becoming more common, the need for receiver implementations to be tested is more crucial now. The basic philosophy of testing is to create a calibrated stimulus based on the worst-case compliance signals parameter that a receiver should see. This test vector is then fed into the receiver PHY. The data pattern transmitted is then compared with the original signal. This is fundamentally a basic bit error rate measurement. In order to do this, you will require a waveform generator that has these abilities. You will need to generate a clock and at least one data lane. You will need the ability to generate and switch dynamically between the low power and high speed modes, and you will need the ability to calibrate the signal, which is typically done using an oscilloscope. When it comes to nitty-gritty of actually making these measurements, there are some complexities and challenges that arise. First, there is often a need to generate multiple test sequences, simulating the different signal modes, pattern, and physical signal parameters. You need the ability to induce controllable noise, jitter, and skew onto different portions of the test waveform. There needs to be a method to do error checking. The CTS document does not mandate any specific tool or procedure to do this, but instead leaves it up to the implementer to find the best approach for their solution. As mentioned in a previous slide, these are a large amount of receiver measurements covering both the low power and HS mode. The signal generator must be flexible and adaptable, and you must be able to calibrate it. Finally, many configurations require complex setups with expensive external components. A proverbial rat nest of amplifiers and BSTs with their associated power supplies are required to create the conditions for both low power and high speed modes. During high-speed testing, it is required to be able to add and calibrate random and deterministic jitter components to the signal. You must be able also to either de-embed the effect of test cable from your signals or embed the effect of channel losses to your calibrated signal. The latest 2.0 version of the specification also requires the need to emulate transmitter pre-emphasis and spread spectrum clocking on the test signal. Finally, it is required to create a dynamic skew between the clock and data signals. In low-power mode, testings require the emulation of noise from dynamic termination switching on the transmitter. This is referred to as E-spike noise. You must be able to stipulate and calibrate these levels. And there is a need to add sinusoidal noise to the low-power signal. Finally, it is required to test the receiver response to minimum and maximum timing parameters during the different state entering and exiting high-speed burst mode. To overcome these challenges, Tektronix employs a high-performance multi-channel arbitrary waveform generator. These are effectively high-bandwidth, high-sample rate, high-resolution digital-to-analog converters with long waveform buffers. Signal impairments and calibration can be done mathematically using a process called direct waveform synthesis. With enough oversampling in the digital-to-analog converters, we can mathematically model the waveform we want to generate. The best way to think of an arbitrary waveform generator is a scope in reverse. Arbitrary waveform generators also have the advantage of being able to generate very repeatable performance without the need for constant calibration, as the test vector is stored in the form of a waveform file. Tektronix solution not only supplies these hardware muscles to create these complex and varied waveforms, but also the software brains to allow quick, customizable setups. This includes the ability to have full control of the patterns, AC/DC voltage levels, and timing parameters. The concept behind the arbitrary waveform generator is simple. A variable frequency clock steps through a pre-stored digital representation of an arbitrary waveform, which is then converted into an analog signal. So, simple in concept, a variety of important considerations are necessary to get the best performance possible from the arbitrary waveform generators for each test application. The AWG is effectively a very fast digital-to-analog converter. It contains a variable clock with 6 decimal point precision, fast DDR memory containing digital values representing each voltage sample points, the digital-analog converter, optional amplifier filters and offset controls, external filtering and amplifications is required. In order to reach the signaling and biasing levels required for both low power and high speed modes, it is often required to have further signal conditioning outside of the AWG. In the past, many implementers have employed banks of amplifiers and bias tees along with the associated power and cabling to achieve this. In many cases, the multi-lane nature of DeFi means we have a rat's nest of components and cables hanging off the signal generator, which is difficult to calibrate. Often, AC coupling specification of these components can make it difficult to reach conformant low-power signals. In these screenshots, you can visually see the challenges involved in the drop-in of the low-power state of the waveform, showing accuracy issues. Tektronix have worked to integrate these components into a single One UI box called the MDC4500, greatly simplifying the solution. This unit supports the voltage range and signal rates required for V1.2 of the specification. It contains signals path for up to 4 differential pairs, making it possible to do multi-lane testing. Also, the use of internal DACs for applying the bias levels instead of bias tees make it possible to meet the LP signaling level conditions mandated by the specifications. To create these stressed signals, Tektronix also supplied dedicated software package called DeFi Express, which is designed to allow the user to generate and calibrate signals to the CTS levels. This tool allows the user to input the impairments such as jitter and noise, as well as emulate channel losses from inter-symbol interferences. The software is designed to support all signaling modes required for DeFi testing through a graphical user interface. It also includes tools such as batch compiling for margin testings, as well as the ability to recognize the integration of the MDC box, set the normalized waveform levels to match the MDC gains, and to control it. Other features of the DeFi Express software include the hardware sequencer, which, together with the batch compile tool, allows users to easily define and compile complex text sequences for margin testing. This can include the DSQ capability of the master and slave, HS and LP signal stressing, and the transition in and out of the HS burst mode, all of which are mandated by the DeFi CTS documents. DeFi Express gives the power of both conformance testing and flexibility of characterization testing in a single solution. Specific example, E-spike measurement measures the ability of the receiver to reject signals with amplitude and direction that is less than a specific limit. This measurement is made on the LP signaling. In our DeFi Express software, we can define the basic signal conditions for a LP state, including the pattern being transmitted, PRBS, Mark 1, Mark 2, stop, ULPS, and so on. We can then set the nominal data rate and Thevenin voltage levels of rise and fall times. Next, we can define the impairments of this LP signal. In this example, we are looking at the E-spike effect, but it could also be adding noise. For the E-spike, we can define the glitch's amplitude and duration, and we can apply it to specific lines in the lane. This pattern is then compiled and can be added to the test sequences. Another example, high-speed receiver jitter testing for lanes above 1.5 gigabit per second requires the testing of receiver ability to accept signals with both static and dynamic skew from a transmitter in the presence of different channel conditions, with up to 20 dB loss at 5 GHz. The test vector is defined by a maximum amount of jitter and skew. The jitter profile takes the form of a receiver eye diagram. The specification also specifies that the receiver should be tested with 3 different channel conditions. The receiver should also be tested under 9 different conditions with different static skews and VCM settings. It is also worth noting that for lanes with data rates above 2.5 gigabit per second on the 2.0 specification, has the requirement to test with spread spectrum clocking and pre-emphasis. Like the E-spike example, the RX jitter measurement allows the user to first define the base characteristics of the HS signaling, including the test pattern, data rate, and voltage levels of the clock and data. Like the E-spike example, the RX jitter measurement allows the user to first define the base characteristics of the HS signaling, including the test pattern, data rate, and voltage levels of the clock and data. Once the base pattern is defined, the user can add jitter in the form of random or periodic jitter. Periodic jitter is typically used to add and calibrate the dynamic jitter. The software also allows the user to open and add the S parameters for the different channels for the clock and data lanes. Here you can see the results. On the left-hand side, you can see the clean base eye diagram from the AWG along with the calibrated test vector after jitter and channel losses have been added. Let's talk about a critical aspect of any receiver testing, calibration. It is imperative to always calibrate your test vectors in advance, and this process can often be more time-consuming than the testing itself. Any signal generator will have its own impairments, and when we add extra cables and components, be it our external components or in our case, our integrated MDC box, these too will add more variations to the test setup. It is impossible for a test and measurement vendor to supply a signal generator solution that will generate clean, controllable signals without some level of calibration. So let's use our MDC box as an example of how this process works. First, let's look at the HS burst when we connect our AWG directly into the scope. Here, I am using an eye diagram to depict the signal quality. You can see the clock signals behind the data signals in the form of an X in the middle of the eye. These signals is pretty clean, but still contains some rise time impairments and noise. Then I add the MDC box, and you can see how its frequency response add noise and distortion to the waveform, reducing my usable margin. The Tektronix solution employs an automatic closed-loop calibration procedure that quickly measures the frequency response of the total setup and then creates a correction filter to remove any frequency and phase error. This will sharpen up the rise time and remove errors on the signal's level. We now have a method where we can accurately correct the signal to the end of my test cables, removing the equipment error and variation due to the cable length variation and the cable wearing out. At this point, the user can then add the appropriate amount of jitter and noise to the signal in order to meet the stringent test requirements of the CTS. So let's summarize the equipment configuration for RX testing. You need at least two channel AWG 70000 O2A or B. That will give you the ability to generate both high speed and low power signaling on both the clock and one data lane. For users with flexible setups or those who are cost sensitive, it is possible to use just a single AWG 70002A or B model to generate low power, high speed data signals with a continuous HS clock. From Tektronix, we will also supply the MDC 4500 to condition the signal levels for low power and high speed modes. An 8 GHz oscilloscope is used to calibrate the arbitrary waveform generator. This is the same model instrument used in transmitter testing. While on the software side, Tektronix has the DeFi Express waveform create toolset, along with the DeFi Essentials tool mentioned earlier to simplify the calibration process. Well, we've covered a huge range of topics. First, we looked up at the technology trends in the automotive industry that is driving the adoption of MIPI standards such as DeFi. Then we spent some time looking at the DeFi signaling itself. And we spoke about what is required for our products to conform with the DeFi specifications. Then we spent a large amount of time reviewing the test requirements and challenges for both transmitters and receivers. And during that process, we looked at how Tektronix provide the complex solution for DeFi TX and RX testing.
And now for the next few minutes, I will give you a live demonstration of the compliance application for MIPI DeFi. I'm going to run this demonstration on the 6 series new MSO oscilloscope. Keep in mind that this application also exists in the 70,000 scopes families. Let's start with the demonstration. So as I explained during the seminar, you will need 4 active probes, probing for D+, D- for the data lane, and clock plus and clock minus on the termination board connected to your DUT. What you will be using here is a 6 series mixed signal oscilloscope with 8 GHz of bandwidth, on which you will be running Tech Express DeFi 1.2 application. So that application will guide you through the pitfalls of making all that standard measurements on the MIPI DeFi. So you can use either live waveform or save your waveform to make a offline analysis. You can select the speed rate you will be using, if the clock is continuous or discontinuous, and if you are running the normal mode or some debug mode. Sometimes we had more features for debugging in that area. You can also select what type of implementation you are running on your board. It can be a single data lane or multiple data lane. And then when you will have set up all of this, you will go to the next step. And in the next step, you will find all the standard measurements specified in the CTS for MIPI DeFi. So you will find all the test names and associated number. And you can see I've selected everything right now. So what I will do is just press run, and the compliance will take full control of the oscilloscope to make the measurement. Here you have a user message that is prompt to tell the operator that he has to connect the 4 probes on the termination board to probe the selected signals. And when you're done about that, you just press OK. And the scope will be resetted completely, and the setup will be proceed to get the proper sensitivity range, the proper filtering, and make all the measurement in an automated fashion. So right now, I don't have a real DUT. I'm using AWG from Tektronix, which is a 4-channel, 5 gigasample arbitrary waveform generator with 16 bits of resolution, and that gives me the freedom to generate typical signals from the MIPI DeFi, so I can analyze them with the oscilloscope. So as we can see, if you would have to do that measurement by hands, you would spend more likely half a day or a day to proceed to all the measurements. In few minutes, you will have the test report generated from this application. So not only you will have a repeatable test process, the methodology for test is completely squared, you will avoid setup pitfalls, and you will have repeatable measurements in a comprehensive report. So you have relays inside the oscilloscope that I use to commute sensitivities. Sometimes they are used to commute termination impedance from 1 megohm to 50 ohm. And sometimes they are also commute to do self-calibration. So sometimes they can revert to internal signals to self-calibrate and coming back to the outside signal. As I explained in the seminar, the DeFi bus requires high impedance and at the same time high bandwidth probes. And Tektronix solved that challenge with the P77 family. This family of active probes is available on 6 series oscilloscope and DPO 70000, DX and SX families as well. What makes this probe unique is the way Tektronix is both manufacturing it, characterizing it, and you get all the performance of the probe simply by using it. The AC response of the probe, the S parameters of each probe has been measured during the factory stage, and they've been stored in the amplifier. So when you connect the probe to the scope is downloading the response of the probe to compensate for it. Same apply to that fancy test points here. So that's the probe heads. We call them ST Flex A. I hope you can see them quite easily. This is amazing. That piece of technology gives you the lowest loading ever with bandwidth from 8 gig up to 20 gigahertz, low loading. And again, the performance of that tip is coming from the fact that you have an active part right there at the edge of the tip, the closest possible to your DUT. So you get the lowest loading possible on your board. The performance of that tip, again, the S parameter, amplitude and phase response, has been characterized unitarily and stored in an EEPROM on that piece of equipment. So you will just connect these two together, and again, the oscilloscope will know that you are using this tip and is going to download the performance response of that very tip and compensate for it. You would think that is expensive. No, it's less than $100. It's less than $100, where the typical tips are more than $1,000 on the market from the competition. So that's very important. You get the performance with the cost reduction. That concludes our web seminar on MIPI DeFi testing in automotive market. Let's summarize what we learned today. You will need a 8 GHz oscilloscope to test MIPI DeFi 1.2. You will need 4 probes in order to measure the D+ and D- leg of the clock and data lane. So 4 8 GHz probes will be required. You will need a low noise oscilloscope to get the benefits of the high dynamic range of the scope, because MIPI D5 involves low power, pulse of 1.2 volt, and high-speed signal with few hundreds of millivolts of swing. So there you will need the dynamic. I hope you found that web seminar useful. For more information, to request a demonstration of a free trial, please go to our website. Have a good day.